So, welcome back to lectures on engineering mathematics 2, and this is lecture number 54 on properties of Laplace transform. So, today we will discuss some properties, and using those properties we will realize that finding or evaluating this Laplace transform or inverse Laplace transform becomes easier. So, there will be today in this lecture we will be discussing the shifting properties, and then we have the change of scale properties and multiplication properties. So, these three properties will be discussed in this lecture. So, coming to the first shifting property. So, if this Laplace of f t is f s, then this property says that the Laplace of exponential a t f t will be f s minus a. So, if we multiply this f t by this e power a t, then there will be a shift in the Laplace transform. So, s will be replaced by s minus a. So, naturally once we have this property, this will be much easier to find the Laplace transform where we do see the multiplication of some exponential function. So, by definition, so we can go through the proof. The proofs are very simple in these cases, because finally we are dealing with this integrals only. So, we have the Laplace of e power a t f t, e power a t f t is now the this function here, and then e power minus s t because of the Laplace transform. So, then we have this f t, and this e power a t will be merged with this e power minus s t. That means, we have e power minus s minus a t d t, and that is exactly the f s minus a, because f s is nothing but 0 to infinity e power minus s t and then f t d t. So, instead of this s, here we have s minus a, therefore, we have written this as f s minus a. The similar result we have for the inverse Laplace transform. So, together with the Laplace transform, we will be also listing here for inverse Laplace transform, because these results are just the analog of the forward properties there. So, if we have the Laplace inverse of f s is f t, so we are just reversing this there. Then this says that L inverse of f s minus a. So, this L goes to the right hand side. L inverse f s minus a will be e power a t f t. So, for finding the inverse, we will be using this shifting property. For finding the Laplace transform, we may use this shifting property. So, coming to the example, so we have first here we want to find the Laplace transform of e power minus t sin square t, for instance. So, here with the function sin square t, e power minus t is sitting. So, that is exactly where we can apply the shifting property. So, first we will evaluate the Laplace transform of sin square t as 1 minus cos 2 t over 2. That means, we have 1 by 2, the Laplace transform of 1, that is 1 by s. So, it is a linearity property we are using of the Laplace transform. Then we have 1 by 2 there with the minus sign, and the Laplace transform of cos 2 t, which is s square over this s square s over s square plus 4. Then we can just simplify this. So, we got this 2 over s square plus 4, and then this is what we call as f s, the Laplace of this sin square t, and then to get the Laplace of e power minus t sin square t, we will apply this shifting property, which is called the first shifting property. So, using this property, we have e power minus t sin square t, and then we have here f s plus 1. So, the s will be replaced by s plus 1 because of this e power minus t. So, here now we have this 2 over s is replaced by s plus 1, s square plus 2 s plus 5. So, we have now the next problem where we want to find the Laplace transform of 2 power t and t plus 3 square. So, again the similar situation, we have the multiplication with this exponential function. So, if we find the Laplace transform of this t plus 3 square, then we can get the Laplace transform of this e power 2 t into t plus 3 whole square. So, this t plus 3 whole square is the t square plus 6t plus 9, and then we can use the linearity property to find this Laplace transform. So, we have the Laplace of t square 6 times Laplace of t plus this 9 times Laplace of 1. So, here the Laplace of t square is 2 over factorial 2 over s cube, then here Laplace of t is 1 over s square, and this Laplace of 1 is 1 over s. So, we have this 2 over s cube, 6 over s square, and then 9 over s, which can be simplified to get this 2 plus 6x plus 9 s square over s cube. Then using this first shifting property, which says that the exponential e power a t f t, the Laplace transform will be f of s minus a. So, now this s in this expression here, the s will be replaced by s minus a, and a in our case is just 2 there. So, that means this 2 plus 6 s minus 2, and then here 9 s minus 2 whole square divided by this s minus 2 cube. So, this is the Laplace transform of e power 2 t sin t plus 3 square, which again can be simplified to finally give this expression here. We want to find now the inverse Laplace transform, for instance, of this function 1 over s plus 1 square. So, in that case we will rewrite this s minus and this a, which is minus 1 now, whole square, and then we can use this shifting property that the Laplace inverse of f s minus a is e power a t and f t. So, here we have this s is just s minus a, that means if we use this property there, so we can have the e power this minus t outside and then the Laplace of 1 over s square. So, e power minus t and the Laplace inverse of this 1 over s square, and therefore, this is e power t, and then here we have this Laplace inverse of 1 over s square as t. So, this is t e power minus t using this first shifting property. For instance, we want to find the Laplace inverse transform of this 1 over s square plus 4 s plus 8. This also can be handled exactly in a similar fashion, that we have this s square plus 4 s plus 8, which is nothing but s plus 2 whole square plus 4. So, this s is just s plus 2 there, and we will now apply the shifting property to get this e power minus 2 t outside, and then the Laplace inverse of 1 over s square. So, this will be becoming now s square. So, s square plus 4. So, that means we have this half. Because of this we need 2 there to have this sign 2 t. So, the e power minus t is there, and then this is half sin 2 t. So, we got this inverse transform using this first shifting property. There is another result which is called the second shifting property, where we have the Laplace transform of f t is f s if this is given, and also the g t is now given by a shift here. When t greater than a, it is f t minus a. So, there is a shift in the function now, and then from 0 to a, where this function is shifted, the value is set to 0. So, we have this again a second shifting theorem, where the shift is done in the function itself. Now, the question is, what is the Laplace transform of g t? So, to Laplace transform of g t is nothing but e power minus a s and f s. The alternate form, which is also convenient to write this g t, instead of g t writing in this way, we can actually write in this compact form f t minus a Heaviside function t minus a. Recall this Heaviside function, when t is greater than 0 it is 1, t less than 0 it is 0, and now this f t minus a h t minus a is exactly this function g t, because when t is greater than a, this will become 1 here h. So, we have f t minus a, and when t is less than a, so this will become 0. So, instead of writing this g t in this way, we can also write this g t in this way, f t minus a h t minus a, and we have e power minus a s and then f s. So, by definition, if we go the Laplace transform of g t, because in 0 to a the value of the function g t is 0. So, the integral will start from a to infinity and the function is f t minus a e power minus s t d t. And if we substitute this t minus a as u, that means d t is du. So, this will become now when t is a, then u will become 0. So, this is 0 and then here we have t infinity. So, u will be also infinity. Then we have f u and e power minus s and t is a plus u dt. So, here e power minus a s we can bring out and then the remaining part is just the f s, the Laplace transform of f t. For the inverse Laplace transform, we have again a similar result. If Laplace inverse f s is f t, so parallel to this one, then the Laplace inverse of e power minus a s. So, Laplace inverse here of e power minus a s f s will be the Laplace transform or the g t. G t is we have written here in compact form, that is f t minus a and h t minus a. So, we have the counterpart for the inverse Laplace transform, which is exactly can be written from this second shifting property. Coming to the some examples. So, we have for instance here you find the Laplace transform of this g t, where g t is cos t minus pi by 3 when t is greater than pi by 3 and 0 in this range 0 to pi by 3. So, the cos function is shifted for this t greater than pi by 3, but the value is exactly starting from 0 itself, because cos t minus pi by 3 is there in the argument. So, here if we take this f t as cos t, we know the Laplace transform of this f t, we have already done this. So, s over h square plus 1 and then the Laplace transform of g t, where we can apply this first shifting theorem, which says e power this minus pi by 3 s will go out and then the Fourier transform or the Laplace transform of f t, that is just the cos t. So, the Laplace transform is s over s square plus 1. So, we are done with this second shifting property, and the application is very easy now, and with the help of this we can directly write down the result just by multiplying this e power minus pi by 3 s. If you want to find this Laplace of this function, which is again a shift here. So, 0 to 1 the value is 0 and t greater than the value is t minus 1 square. So, the function is t square and there is a shift this by 1. So, again we can use the second shifting theorem property. So, f t is t square and the Laplace of f t means t square is 2 over this s cube. So, the Laplace of this g t will be e power minus s. E power minus s is coming because of that shift theorem, because here there is a shift by minus 1. So, e power minus 1 s and then the Laplace transform of this f t, which is 2 over s cube. Well, so we can also look at the inverse Laplace transform, how to apply this property of the Laplace transform for the inverse case. So, we have for instance here f s as e power minus s and s square plus 1 into s. So, just to recall that this e power minus s can be adjust with this inverse property or with this second shifting property. So, we need to get the Laplace inverse of 1 over s and s square plus 1, where we can do the partial fractions. We have already discussed yesterday that this is one of the techniques to find the partial fractions. So, 1 over using to find inverse Laplace transform. So, here 1 over s and minus s over s square plus 1 will come, where we can apply this linearity property on this 1 over s. So, L inverse 1 over s and then we have there L inverse s over s square plus 1. So, the L inverse of 1 over s is 1 and the L inverse of this s over s square plus 1, this is cos t. So, we have this 1 over cos t, the result of the Laplace inverse of 1 over s and s square plus 1. Now, getting to the Laplace inverse of e power minus s with this s into s square plus 1. So, we will apply this shifting theorem that says that L inverse e power this minus s and then the Laplace of 1 minus cos t, because this is the Laplace inverse of this is 1 minus cos t, that means the Laplace of this. So, this is what given here, that e power minus s and the this some kind of f s is given here. The second shifting theorem says that e power minus a s f s. So, here we have e power minus s and this is our f s here, which is 1 over s square plus 1, and the result is f t minus a h t minus a. So, the f t here is simply 1 minus this cos t, and then we have to shift this by this a. So, a is 1 in our case, and then h t minus a will also come together. So, we have 1 minus this cos t, the t will be shifted by 1. So, t minus 1, and then this Heaviside function h t minus 1. So, using this second shifting property, we can now deal such functions where e power minus s is appearing in the multiplication. So, this e power s is handled here by this shift t minus 1 and multiplied by h t minus 1. One more example to find this to apply this inverse to apply this second shifting property on this inverse Laplace transform. So, we have f s e power minus s s square plus 4, e power minus 2 s s square plus 4 and e power minus 3 s s plus 2 whole square. So, again here, because this e power minus s or minus 2 s or minus 3 s appears in the multiplication. So, we will just get the Laplace inverse in this first case 1 over s square plus 4, here we will get 1 over s square plus 4. So, the same thing, but here the shift is different, and here we have s plus 2 square. So, getting the Laplace inverse of this, we can apply the shifting property to get this desired inverse Laplace transform. So, this Laplace inverse of 1 over s square plus 4 is half, because one can multiply 2 there and divide by 2 there. So, this is exactly the sin 2 t, and then this half has to be there. The second, we need to get this Laplace inverse of 1 over s plus 2 whole square. So, s plus 2 whole square is we know already, because of this 2 we can have this shift property which says it is e power minus 2 t, and then 1 over s square, that will be just t. So, with the Laplace inverse of this 1 over s plus 2 square is t e power minus 2 t, using the first shifting property. So, we have used here the first shifting property, and now we can get this inverse. So, Laplace inverse e power minus s s square plus 4, e power minus 2 s s square plus 4, and in this third place we have e power minus 3 s s plus 2 whole square. So, here the shifting property is that e power minus a s. So, this a in our case here it is 1, and here a is 2, and here a is 3. So, we can have a direct shift there by a in f and then multiplied by h t minus a. So, in this case we know that this is half sin 2 t, but now t will be replaced by t minus 1. So, the first situation here is dealt with 2 t minus 1 h t minus 1. In the second case it will be h t minus 2, and this sin 2 t will be sin 2 times t minus 2. In the third place we have e power minus s. So, there will be a factor here h t minus 3, and everything will be replaced by t minus 3. So, here the function was this t. So, the t power minus 2 t. So, t will be t minus 3 and exponential minus 2 t minus 3. So, at every places we have this minus 2 t minus 3, and here also t is replaced with t minus 3. Well, so we will come to the another property, which is the change of scale property. So, the change of scale property says that if Laplace of f t is f s, in that case the Laplace of f a t. So, instead of t, now if we have a t there, then we can just adjust here 1 over s and the Laplace transform this f s, where s is replaced by also s plus s divided by a. So, here also we can use the definition to prove to get the idea how this property is coming up. So, we have Laplace of f a t, the Laplace of f a t, then by definition we have e power minus s t and f a t d t. So, if we substitute this a t equal to u, that means we have a d t is equal to d u. So, now we have to now replace this t by u by a. So, here we have this t there, that is replaced by u by a, then we have f u, and then d t will be d u by a. So, d t will be d u by a. So, and so here it is u. So, we have now if we think this as e power minus s over a and then u, and then we have here f u, letting this 1 over a outside, we have 0 to infinity, and then we have d u. So, looking at this f s now, instead of s we have this s over a here, otherwise this is f s over a. So, here 1 over a f s minus a is coming as a result. Looking at this counterpart for the inverse Laplace transform. So, we have a similar result, that if this L inverse f s is f t, then L inverse f a s. So, here also s is now a s, then the result will be 1 over a and f t over a, because here if we set in this relation, let us say 1 over a we take as b. So, what will happen now here, the Laplace of f t over b will be b and the f b s, or if we take the other side now this Laplace. So, the Laplace inverse of this f b s will be 1 over b and the f of t over b. So, we have this property for the inverse, that the Laplace inverse of this f a s is 1 over a f t over a. Coming to the examples, so we have the Laplace of f t is given as s square minus s plus 1 to s plus 1 whole square and s minus 1, and then we want to find the Laplace of f 2 t. So, we will use naturally the scale property, which says that the Laplace of f a t is nothing but 1 over a, and the Laplace transform of this f t we have to replace s by s over a. So, here we have to now get for Laplace of f of 2 t. So, just applying directly this result, we have to replace this s by 2. So, s will be replaced there by s by 2, and there will be a factor sitting outside as 1 by 2. So, this Laplace of f 2 t will be 1 by 2, this factor 1 by a is coming, and then s is replaced by s by 2, here also s by 2, then 2 s, then s by 2 plus 1 and s by 2 minus 1. So, we have directly applied this result to get this f 2 t, and on simplification of this, what we will get, the Laplace f 2 t will be 1 by 4 there, and this will become s square minus 2 s and plus 4, because this is s square by the numerator is s square by 4 and minus we have s by 2, and then we have 1 there, and here we have this s plus 1 whole square and then s minus 2, and this 2 will go up there and we have 1 by 2. So, this 2 gets cancelled and this 1 by 4 we take common. So, we get s square minus 2 s and then plus 4 will come and we have s is plus 1 square into s minus 2. So, it was a very simple application of this scaling property. If we have now the L inverse s over s square minus 16 given as cos hyperbolic 4 t, then we need to find L inverse of s over 2 s square minus 8. So, we have to again see that what kind of scaling is done in this Laplace transform and then we can apply this scaling property of the inverse transform. So, what we notice that this is given already s over s square minus 416 as cos hyperbolic 2 t, and we know this scaling property that L inverse of f a s is 1 over a f t over a. So, we have to just see that what is the scaling done from this s over s square minus 16 to get this 2 s square minus 8 over s over 2 s square minus 8. So, it is clear here that if s is replaced by 2 s, then what will happen? We have 2 s there and we have 2 s square minus 16, which is s over, if we 4 we take common or we take 2 common from there. So, we have 2 s square and that 2 will get cancelled then with this when we take the common here 2. So, we get still 2 s square and minus 8. So, this is exactly the scaling done here. S is replaced by 2 s, that means our a is 2 now. So, a is 2 here. So, the result will be the Laplace inverse of this will be just 1 over 2 and the f which is already there t by 2. So, using this property we will get this half and cos hyperbolic and this t will be replaced by t by 2, that means we will have instead of 4 t we will have just 2 t. So, the Laplace inverse of this s over this 2 s square minus 8, the desired one. So, this 2 gets cancelled there and we have exactly 2 square minus 8. So, this is half cos hyperbolic 2 t. The last result or the last property here in for today's lecture when we see this multiplication by t power n. So, we have this Laplace transform of if f s is the Laplace transform of f t, that we have the Laplace transform of t f t. So, we can get t f t as minus d over d s f s. So, that is another nice property, and its generalization is that because if we apply repeatedly we have the t power n f t, just minus 1 power n will come out and we have these derivatives there. Looking at this result, we can see that f s is this e power minus s t f t d t, and if you use the Leibniz rule of differentiation. So, if we differentiate here d f over d s, that means here also we have to get this d over d s. So, as a result of this d over d s of this minus t will come out and then we have e power minus s t f t d t. So, this is the Laplace transform of this t f t and this minus sign because of this, and now the function is t f t instead of f t. So, we have this right hand side with minus Laplace of t f t, and that is exactly the result we want to prove, and this repeated differentiation here can give us this general rule which says the t power n is minus 1 d power n over d s n, because if we differentiate again this here. So, we will get d 2 over d s 2 and then here we have again d over d s. So, this minus t will be out, that means minus t square will be coming. So, this minus t will come out of this. So, it will be t square. So, this Laplace transform of t square f t will be just d 2 over d s 2 f s. So, we can get all these general rules, and getting to the inverse Laplace transform, it is other way around, that the Laplace inverse of d n over d s f s is minus 1 power n f n and f t. So, here we want to find the Laplace transform for instance of t square cos a t. We know the Laplace transform of cos a t, and then applying this rule 2 times. So, or directly this d square f s. So, we have to just get this derivative of s over s square plus a square, which is simple, and we can get this in 2 times. So, on simplification we will get it is a 2 s square minus 3 a square divided by s square plus a square power 3. If you want to find the inverse Laplace transform of these functions for instance, and again we will apply this property. So, we have d over ds. We should notice that d over ds of a over s square plus a square is this function here with minus sign, and if we take their s, this is actually this function with again a minus sign. So, we know the result that d over ds of this f s is minus t f t. So, we can apply this result there to get the inverse Laplace of these given functions. So, if we apply here the Laplace inverse of this 2 a s over s square plus a square, which is the derivative of this f s. So, we have the minus sign there and t, and then we have this f t, that means Laplace inverse of a over s square plus a square, which is sin a t. So, here we have sin a t and t sin a t. Similarly, for the second case we have just the inverse of this minus s over s square plus a square, which is t cos t. So, here also we have applied this result of the derivative of this f s is equal to minus t f t. So, these are the references we have used for preparing this lecture, and just to conclude, we have discussed here the shifting properties, which where there are 2 shifting properties. The first shifting property e power minus a t f t, then there will be a shift in the Laplace transform, and if we have a shift here in the function, then there will be a component here e power minus a s outside of f s. Change of scale properties. So, if we know the Laplace of f t, we can get the Laplace of f a t by 1 over a and f s over a. This f is the Laplace transform of f t. This multiplication property, where t power n f t, the Laplace transform of this is nothing but minus 1 power n and nth derivative of this f s with respect to s. So, that is all for this lecture, and I thank you for your attention.